Hello there, Math 126 students. I'm just going to talk through the spring 2025 exam. I'm not going to solve every problem. I just want to quickly talk through them, give an initial start. And if you have follow-up questions, you could ask me either on the discussion board or even better in person this summer. Okay, so first page was these multiple choice. This one was fairly quick, because it says find the radius of the sphere that goes through this point and has center here. So they're telling you the center, and they're telling you a point on the edge. So it's really just a straight distance formula. Success. So that was faster. This was that projection thing. We kind of mentioned in review, a little more of a challenging question in that it's easy if you try to visualize. And this was this idea of, if you're projecting onto the vector A, you can use any vector, longer or shorter, and it will still give you the same thing. So the fact that 1, 2, 3 is also in the direction of A, you can actually put it in here and it doesn't change anything. So that was that clever idea. If you double the vector, it's still pointing the same way. So all of these vectors point the same way. And so when you project B onto this vector, you still get the same thing. That was that whole idea. A and B are unit vectors, which of the following cannot be this. So I tried to think about this question, if, just coming at it in general. I tried to think, could 0, 0 happen? Well, that only happens if the vectors are parallel. Oh, well, they could be parallel. The other thing I would do is I would write this thing down here. These would have been my first things to say, every fact related to the cross product. I mentioned this in my video about how to approach multiple choice questions, which is to write down any related fact first and then try to think of counterexamples. I mean, here I started to think of examples and those worked, and then I wrote this out and then I went, oh wait, the biggest this can be. So that's when I started to think, okay, that happens, that can happen. Is there anything I can say from here? Well, I can say the biggest this can be is when sine is 1. And since they're unit vectors, this is 1. So it can't be longer than length 1. And that's how I came to figure this out. But I think students, should have been kind of debating between these two. And then running some examples. So I think there was other ways you could get at this answer. What point lies on this? So this was sort of a direct question of find the equation of the line. And you can do that fairly quickly. So if you, it goes through these 2 points, so you could immediately get this. And then you could go through and just one by one test and see if the points were on there. If you don't remember how to test, it's not really test. If you don't know how to use your equation of your line, here's how you use it. You put those in with whatever you're trying to intersect with. In this case, we're trying to intersect with the point, and then you solve for the t. And the question is, does it give the same t for those points? So in order for x to be -1, t has to be -2, but that does not make the other two things 5 and 7. So you just keep going. That's what I did. And when I got to the second one, it was correct. Okay. So that one definitely I would have found the equation line. So this is kind of keeping with this theme of, if I don't know what to do, I write down every fact we have related to this. It talks about a line. I give the equation of a line. Talks about a projection. I guess I didn't write down the formula for projection, but I did visually write. And then I try to think of examples. Okay, last one. Which of the following planes is parallel to this? So this one we can do directly. This is the picture I always draw. We want the plane to be parallel to the line, meaning that always the same distance away. And that means the direction vector actually is perpendicular to the normal. So that's the easiest way to test, is that I wanted 1, 2, 3 to be perpendicular to the normal. And the only one where that was true was the last one. Okay, let's keep going. We had a translation question. So I talked about how when we do these sorts of questions, I would translate as follows. So we want the distance from a given, these points, to the x-axis. And this is what it means to be on the x-axis. And this is what it means to be closest. And this is how I always answered these. Distance from x, y, z to 0 or 2. So we want those two things to be equal. We simplify, I did expand this. A bunch of stuff cancels, and you get a cylinder. You actually get a parabolic cylinder. Okay. Parameterize. This one was meant to be quick. So here we can parameterize. And then we can, the only thing we don't know is x. So we can substitute. And we get this. Some people tried to parameterize with square roots, which we allowed, but you had to make sure you dealt with all of the things correctly. This is something you can completely check. Like you can check your parameterizations work in the equations. This one was partial derivatives. I do see students making quite a few little mistakes on derivatives. We got to clean that up just because those are not going to go away if you go on to Math 207. So it's got me thinking that I'm trying to think about what resources I can provide to help students review this skill. But anyways, you take the derivative with respect to x, you take the derivative with respect to y, you evaluate, and then the next question said plug in some numbers to it. Plug in this for y, plug in this for z, and figure out what x is. People did very well on that problem, so I'm not going to say much more. Here we had one of these. This is very similar to that homework question, but a little bit nicer. The homework question where you were trying to find the volume of the biggest box underneath this plane. That was that question we talked about and did in class, and it was a review question. And we talked a lot about it on exam too. But the biggest thing here was if the question says find the volume of the largest box, we should be thinking this right away, and that guides the entire problem. So if you miss that idea, you're not going to get very many points here. This is what we're optimizing. And this is what x is, and what y is, and what z is. And they're telling you that this point, the x, y, z point, is on here. So this one kind of directly gave you the constraint. We're given that the x, y, z has to come from here, which allows us to substitute. The rest of it becomes partial derivative game. So expand, take the partial derivatives, look to factor first. X and y can't be, well, they could be 0, but then it wouldn't be a very interesting box. So then we combine these two, you get, so I saw a lot of people do a rather long bit of solving here. So anyways, you get x is 3, plus or minus 3, but only the positive 3 makes sense. You plug that in here, you get y. You can plug it back in and get z if you want. But the question wanted the volume, and so I plugged that into my function, and that's how I got this. Your justification could be saying something about the boundaries, something about how it can't be 0, and this is the only critical point that's not 0, or you can do the second derivative test. All right. Then we had this one. I think this was probably one of the more challenging questions to get full credit on the test. So if you got most of the credit, you did well. Quite a few people missed a few points. The people that missed bigger chunks didn't know the conceptual idea, which was step 1, we're finding volumes to these surfaces. Step 2, we draw the region. So we have a very clear approach. A few people got the order mixed up. I'll talk about that in a moment. But your immediate step, after you set up the integrands, your immediate step is to find when do these intersect. We talked about that as being an important part of our process. So I did that when I substituted the z's. I moved everything aside and I'm like, oh, this is a circle. You might say, well, that doesn't quite look like a circle, but we had quite a few of these back when we were doing polar. So I completed the square and I went, oh, it's this circle shifted over one. At that moment, you could figure out which one's on top. I saw students plugging in random points that weren't in the region. If you're going to plug in a point, I would plug in 1, 0 to both of these functions. If you have trouble thinking about or visualizing them. So for example, if you plug in 1, 0 to this function, you get 2. If you plug in 1, 0 to this function, so this is 1, this is 1, this is 0, you get 1. Okay, so this is smaller. So I'm going to subtract in this order over the region. You do need to check something inside your region. Checking something on the boundary doesn't really make sense because we already know they're equal on the boundary. That was the point of this. So I did see students trying to plug in points, but they weren't plugging in points that were in the region. And so they got their order flipped up. It was a small deduction, but anyways. And that makes it easier to put them together. You end up getting this when you subtract. Oops, I made it so you can't see. Okay, so then the rest of the question was really about converting, and there was a tricky little note at the end. So converting. Let's convert this. It's easiest to convert it in this form, as we saw in the homework, because then you can just say r squared, and this is r cosine of theta. You can divide both sides by r. Okay, we saw that quite a few times. That's this length from the inside to the outside. And so when we go to integrate, we already know that this is going to be the integral from 0 to 2 cosine of theta. Now the challenge is the rest. So this is going to be 2r cosine of theta minus r squared, r d theta. Now, I sort of sympathize with students that missed this part because it is very tempting to say 0 to 2 pi. And so that was, I feel like that's the biggest challenge in the problem. If you do 0 to 2 pi, you're actually getting double the volume, and it's incorrect. And that's because when you go to plug in values to this, so if you plug in 0, you get a 2. If you plug in pi over 2, you get a 0. So already, when you get to pi over 2, you've done half of this thing. So one way to do this problem is you could just say 0 to pi over 2 times 2. Some people did it that way. Now you got to be careful that there's symmetry, but there is in the surfaces. But when you plug in pi, you're actually all the way around. You've already done it. So I'll say something about what our intended answer was, but I accepted this answer. It actually is correct. Because it gives negative r's, I'm kind of inclined to choose values of theta so that I get positive r's, which would be here to here. But if you do 0 to 2 pi, you're actually double counting. So that was a challenge. You had to actually think about those bounds. But everyone faced that challenge. So a lot of people missed a couple points there, either because of getting these in the wrong order or this out here. And again, I think this was the major challenge. That would have been easy to miss. Then we had a center of mass question. It says that the region is in the first quadrant. So I would, and it's a circle. So I would immediately do polar. And that's 0 to pi over 2 and 0 to 2. So the rest of the problem becomes calculation. I would have probably done the density first and seen that it's 3 pi. And then I would have picked the other one. Now, to save myself time, I would have realized that there's symmetry here and that the density is symmetric, meaning it's the same on both sides. And so that means I can compute just one of them. I also, at the end of the problem, would have checked my work to see if it was reasonable that the point is somewhere in here. Okay, so what do we have? So here's me just straight computing. It actually comes out nice in the fact that the theta and the r are completely separate. Now, I didn't do a lot of this in class. This is me just being a little optimal in my solution. But anyways, you get this number. You get 8/3 plus 32/5. I got a common denominator. There we go. We accept it if some people didn't simplify. So at that point, I really would be done if I recognize the symmetry. So it's going to be this divided by this. And that's what you see down here. But you also could compute the other one, sort of verify you get the same thing. Okay. Then we had take a bunch of derivatives. I did see a few people doing really complicated derivatives here. Now this is similar to homework, so they made their lives a lot harder. But ultimately, just plugging in. The fourth derivative, I don't need till the next part. I don't know why this should be 4 here. So I plugged in my numbers. I got 0, 1, -2, 8. Okay, that's done. I took the fourth derivative on this interval, the biggest it can be. Now, some students forgot absolute values. You shouldn't get a bound of a negative. You can't say the error is less than or equal to a negative. That would be unusual. So anyways, you slap the absolute values around this. The biggest it can be is when the denominator is smallest, which is at 1.8. So you get this pretty large m. You plugged everything in. You got this bound. Students did pretty well on that. Last one, a fairly quick one. You're using the series for sine. This is what the series for sine, what the coefficients are. And then you're plugging in a 2. So we're plugging in a 2x to the third to the 2k plus 1, which is 2 to the 2k plus 1, x to the 6k plus 3. But because the x on the outside, you get this. Remember when we talked about this, that this meant we're looking for when the exponent here is 16. So we solved, we got a 2, we plugged in a 2. And then remember that the connection was that this thing in front should match up what we would have gotten using the derivative method. Okay, so we put in a 2, we get this, they're equal, so we can multiply both sides by 16 factorial, and that'll tell us what this is. That's this answer. And then lastly, we had a problem where you had to give the first few terms. When you plug in 0, you get just 2, x to the fourth. And when you plug in 1, you get negative 2 to the third, 3 factorial, x to the 10th. And then you integrate, done. So there we go. Hopefully that gives you a little bit of an idea. Again, follow up with me this summer would be great. And we could discuss any further questions you have.